In the last problem, we were given the percent dissociation and asked to calculate the Ka, and now we're going to do the opposite. We've got the Ka, we want to calculate the percent dissociation. So we're going to start with our equation. I've got acetic acid, C2H3O2. In solution, the only other particle present would be water. Now this will dissociate. As an acid, we are a hydrogen donor, so I'll be left with the acetate ion, H3O2 minus, and hydronium, H3O plus. So I'm going to set up an ice table. When I'm working with weak acids and weak bases, my mind thinks ice table, and I know this is weak because the Ka is pretty small. All right, so I've got a 1 molar solution. I'm not going to use the water, and initially my ions would be 0. Now, without having the percent dissociation, I do not know how far forward to shift this. So now we got to say minus x and plus x and plus x. So that at equilibrium, this will be 1 minus x, x, and x. Okay, so eventually x will be used to calculate my percent dissociation. But I gotta figure out what x is. But I can do that as long as I've been given the Ka. So let's see what we got here. The Ka is 1.8 times 10 to the negative 5th. And again, as many of these ice tables, as you see with weak acids and weak bases, you'll find some commonalities. And the two ions are always going to be a 1-to-1 ratio, so it's x squared on the top, and then you'll have the original concentration of the acid or base minus x. So if you wanted to simplify things a little bit, we could say x squared over 1 minus x. And now I just got to solve for x. But we also said there's a little shortcut here in that the K value is small, and so x is going to be small. Yeah, we're going to go forward and dissociate, but not by much. And so in a sense, we're kind of saying maybe 1 minus x is kind of irrelevant. If x is going to be something small, and I'm always leaving like a reasonable number of sig figs and decimal spots, that maybe we can just ignore that minus x in the denominator, which we'll always be able to do on the AP test, because otherwise we would have to solve this with the quadratic equation, and we don't need to do that on the AP exam. It's not a math test, it's a chemistry test. So we can get rid of that minus x, and the reason behind that is because x is going to be really small, and it's probably insignificant with a reasonable amount of sig figs or decimal spots, which then makes this a lot easier to solve, right? I'm going to cross multiply and take the square root. And I get x to be 0.00, let's go with 3 figures, 424. We were given 3, so I'll leave 3. There's my x, and yeah, it is tiny, it's small. All right, so now we can do this percent dissociation. Percent dissociation is the amount ionized or the amount dissociated divided by the original amount of acid. Here it is. The amount dissociated divided by the initial concentration. That makes sense, right? Wrong direction. Here we go. So it's going to be my x value. That's the amount dissociated. 0.00424 divided by the initial concentration, which is 1. These are both molarities. I'm going to multiply by 100 to make it a percent. And yeah, this is small, like 0.424%. Less than 1% of those acetic acid molecules dissociate. Isn't that crazy? Super tiny. So yeah, this is a weak acid. Now hopefully that kind of makes sense, because now want to throw a wrench into it. Most people can get that far and they're like, oh yeah, that makes sense. I get it. A percent is the part divided by the whole. So yeah, it's like your X value. It's the amount of the original acid that dissociated divided by the initial amount of acid that I had. All right, so now I'm going to make it weird on you. What if I did this whole thing, but with a different molarity? What if instead of it being 1 molar, I make it 0.1? What if I change this to 0.1 molar? Now everything's going to stay the same except for when we get to this equilibrium line, it would just be like 0.1 minus X. And so let's say I was solving for X. Okay, I'm going to have everything really similar again, but down here in the denominator, this would be like 0.1 minus X. I can still get rid of that minus X because the K value is still tiny. K values are only temperature dependent. So as long as we're at the same temperature, that K value is always the same. Now, unless they tell you otherwise, we're going to always assume that we're at constant temperature. So everything's really similar. I'm just going to cross multiply, take the square root again, and I'm going to get just a slightly different value. Here in red, with the 0.1 molar solution, I would get an X value of 0.00134. So this would be in the 0.1 molar solution. Okay, so you can kind of follow the calculations, and then a lot of it stays the same. It's really just that initial concentration that would be different. I cross multiply, take the square root, and I get a smaller X value. Interesting, right? Well, let's calculate the percent dissociation. So far, you're probably thinking, okay, yeah, that makes sense. Maybe that if the original concentration was less, then I'm going to get less hydrogen and acetate in the solution, right? That, we're going forward, and X technically does represent the concentration of those two ions. So if the original solution was more dilute, less concentrated, that makes sense that I would end up getting less hydrogen in the final solution, or less hydronium. I bet this would make sense too while I'm thinking about it. What if I were to do the pH? Whoa, let's get crazy and calculate the pH. Let's say I do the pH in the 1 molar solution. And so X is the concentration, woo, of hydronium. So I go opposite log of 0.00424, and I would get a pH of 2.37. And let's say I do that again in the 0.1 molar solution. Opposite log of X, because again, this X value is the amount of hydrogen or hydronium. 0.00134. Opposite log gives me a pH of 2.87. So all of that seems to make sense, right? In a less concentrated solution, a more dilute solution, there's just not as much acetic acid to begin with, so there's not going to be as much hydronium or hydrogen produced. X is smaller, so the pH is larger, which really again means that there's less hydrogen or hydronium in the solution. So far that's all really cool, right? Everything makes sense. But now watch this. Here's the part that gets a little bit hairy. What if I do the percent ionization? I'm going to take my X value, 0.00134 divided by the initial concentration, 0.1, those are molarities, times 100 to make it a percent. I get 1.34%. So everything made sense until maybe now the percent ionization has increased. What? The percent ionization is greater. Oh, brother. So this is something that's been coming up on the AP test recently as well, where they want to know, like, how would the pH compare? And so, yeah, we would say in a more dilute solution, the pH will be higher. There's less hydrogen, hydronium. And obviously the same thing would be said about a base. And there would be less hydroxide in a more dilute solution. But the percent ionization increases. And it's really that it is a percentage. And here's one other way of thinking about it. Like if you were to do a Q versus K, oh gosh, where am I going to squeeze it? Let's squeeze it in here. So I had the original K value, and so now it's like I diluted the solution by 10-fold. So what if I were to say then like 1/10 of X, 1/10 of X all over 1/10 of the original. So here's kind of my comparison. The original was 1 minus X. In the more dilute solution, everything goes down by 1/10. But then do you kind of see what we would get here? We could write this, oh my gosh, I'm going to squeeze it in here, as maybe Q equals, if I simplify this, 1/10 of K. Oh boy, this is big. Q is going to be smaller than K, because look what happens in the numerator. I've got like 1/10 of both ions, and then in the denominator I've just got one particle. So yeah, I mean, I could kind of simplify this, and I'm going to get that Q equals 1/10 of K, or that Q is less than K. And we've always said when Q is less than K, the reaction's going to shift more forward until Q equals K. That this ion product is going to be too small because it's a product of both ions being 1/10 of the original. Oh, so in a dilute solution, the percent of the original molecules dissociated does increase. And it's because Q is too small. And now we want to get to a point where Q equals K. So we're going to shift this thing forward a little bit more until Q can equal K. Even though everything else is also true. That's the only thing that's a little bit wacky, is that the percent ionization is greater, but the pH is less acidic. And the pH is greater, but that again means that it is less acidic. There's less hydrogen in the solution, but it's because there was less molecules to start with. So again, something that'll come up on the AP exam. It's something that's kind of tricky. So reach out if you have any questions, but there'll be some great practice questions posted to help you along.